Jesus Franco is a chemical engineer from BUAP and a master's student in digital systems at Citedi-IPN. His multidisciplinary background bridges material science and AI during his undergraduate studies. He worked on synthesizing silver nanostars, and now his research focuses on AI-driven advances in material science, including property prediction in metallic glasses and fifth-SEM image processing of tantalum carbide using GANs. He has also explored generative quantum models. Committed to conservation, he applies his technical skills to ecological challenges, such as graph-based identification of sea turtles. His goal is to push scientific boundaries by integrating AI, quantum computing, and signal processing to solve complex problems in materials innovation, biodiversity, preservation, and beyond. Without further introduction, Jesus Franco.
Hi everyone, my name is Jesus Franco, and today I'm excited because I'm going to present you my project titled Lightweight Graph-Based Methods for Sea Turtle Identification. So the table of contents is the next. In the first part, I will cover the photo identification of sea turtles, the photo identification approaches, the distinctive markings in sea turtles, the graph-based methods, the study area, and the acquisition. In the second part, I will explain you about the methodology to convert the image to graph. In the second part, the morphological graph encoding using 3 techniques. And finally, the overall architecture. And in the third part, I will discuss the results and the discussion. So let's start with the introduction. Okay, for identification of sea turtles. What is the idea of that? First, I'm working to identify each individual. I'm not working to identify if this is a dog or this is a cat or the specific species of the individual, like if this is green turtle or black turtle. No, I'm working to identify the specific individual. Okay? So the photo identification is crucial for sea turtle conservation by enabling automated individual recognition. So the idea is, for example, if someone take a photo of an individual in a coast in Thailand, for say something, and then other person the next year take a photo in the Gulf of Mexico, and with just a photo you can identify the specific individual, will help us to tracking and support the large-scale population assessments. Okay. So other thing is that promotes the community participation in conservation. Because the main idea of the project is to create a model that identifies individuals just with a photo, with no specific image requirements. Okay? And the traditional photo identification methods are labor intensive and resource limited. I'm going to explain more about it. And also, other important thing about the sea turtle is that the photo identification of sea turtle is not invasive methods. So this is a good method in general. Okay, there are 2 main approaches for photo identification. The first one is the future engineering handcraft methods. Is with the expert define the specific descriptors of the individual. For example, if this individual have a specific skewed in some part of the head or the flipper or something similar. Also use external comparison, so that means that use separate algorithms for the identification of the specific individual. Also is quality dependent. That means that require a specific image information and consistent photography. The other approach is the end-to-end deep learning. Is automatic future learning. That means that the model automatic extract and learn the parents from the data, from the individuals. Also, the future extraction and the classification are in the same model. And also is robust to variability, handles real-world image difference effectively. Okay, so my project is in this approach, graph-based representation. But one thing about these approaches is that require a specific characteristic of the image, also have problems because all of these models require high computational cost. So in my case, in the graph, it's more efficient for the computational cost, and also handles the real-world image difference effectively. Okay? So this is the idea. Use graph instead of the raw image. Okay. So each individual have specific markings, specific patterns, as the humans. Okay, so each human have a specific feature to identify. Okay, so this is a morphological singularity of the head, of the flippers, of the carapace, in general, of the individual. So the idea is use graph to extract these distinctive patterns from seed-to-roll image using this architecture. Okay, so this is the general idea. Extract the information and use graph for this task. So the graph-based methods have some advantage. For example, is the computational efficiency, because I'm working with graph instead of the image, so it's better for the computer. For his adaptability to real-world condition, because it's resistant to variable lighting and angle change. So this is better for the image because we can take the photo in different angles and the model will recognize the individual. And also the long-range feature analysis, because capture anatomical relationship between distant features of the same individual. Okay, this is about the study area and data acquisition. The database is of 21 individuals of seed totals. For each individual, we have 6 photos. As you can see, it's a small database. This is some image from the database. Also, you can see the difference between each image. We don't have a specific feature for the image. And the main idea is to translate each photo into a graph, and with the graph, we will train the model. The data set were collected in the Santuario de Rancho Nuevo in Tamaulipas. We are working with a specific species of seed turtle. We are working with the Kempis ridley turtle, which is endemic of the Gulf of Mexico and Mexican coast. Also, other important thing about the seed turtles is in Mexico we have seeds of the 7 species of seed turtle. So we have a big importance for conservate these species. Okay, so let's continue with the methodology. Okay, this is the idea. First, we have the image. Then we divide the image into 150 segments using a slick algorithm. And finally, create the graph. With the segments are represented as nodes in a graph, establishing connection between them. Okay? So the idea is if a person, a user, take a photo, my model automatically convert into a graph, then add to a graph neural network model, and with this model will give us the specific identification, the specific ID of the individual, okay? Other thing is that we have 3 ways to create the graph that I'm gonna explain. This is the first way to create the graph, region adjacency graph. In this technique, RAG emphasizes continuous spatial relationship. So the nodes are connected only to the immediate neighbors. And with this technique, preserve the local structure relationship. So this is the general formula. Each node will connect with the more closest neighbors in the top, bottom, left, and right. Okay? The second is the KNN, the K nearest neighbors. In this case, impose a fixed number of neighbors of each node. Okay, selecting the closest one. This ensures the uniform graphic complexity regardless of variation of the input image. As you can see here, we have here 3 neighbors and 5 neighbors. And also, when we change the number of neighbors, increase the complexity of the graph and the density of the connection. This will help us to give more information to the model. Okay, so finally, the adaptive local similarity graph. This is my own model. ALCG connects nodes only if they have 2 criteria. The first one is the feature similarity if 2 nodes have similar intensity of colors, and the second, the spatial proximity. That means that it's close one to other, okay? So this dual connection approach enables the precise grouping of anatomical total regions. So this is a general rule. We have a threshold in each case. If we have the similar intensity and if one node is close to the other node, we'll make the connection. And also, as you can see here, the graph create like zones. Here I create a dense graph in the heat and other graph in the environment. In this way, we can give different information to our model and learn more about the parents of the individual. Okay, this is the overall architecture. At the beginning, we have the photo. Then we had 3 different ways to create the graph: the ALCG, the RAR, and the KNN. After that, we have the future extraction of the information of each graph using residual connection that is for reuse information and give more information to the model, and concatenation that combines information. And finally, a neural network. Okay, so with this approach, we can use different ways to create graph, extract information, and the neural network to obtain the better performance of the model. So let's discuss the results and discussions. But before of that, I want to show you about the number of edges, because in each way to create the graph, we have different number of edges in the graph. Okay, so the base models is the KNN5, the RAR, and the ALCG with a fixed threshold. So as you can see here, have a huge variability of the edge. So I think what happens if I give more restriction to the model? For example, in the ALCG, make a different thresholds to change depending of each image, or for example, in the RAR or in the KNN, adding a rule about the intensity. Yes, with this approach, decrease the number of variation of the edge between the graph. But we increase the computational cost, and also we don't increase the performance. So for this reason, I don't use that. Just I explore just to clarify if this is a better approach. So finally, I only use the main or the base models. And as you can see here, by analyzing multiple configurations with different ways to create graphs, to extract information, to give information to the nodes, and in the neural network, we achieve a validation accuracy of 52%, which is an amazing result. Because remember that we are working to identify the specific individual of the seed total. So it's a hard task. And also, if you remember, the database is so different. So it's really hard task. And we have a good performance until now. And we are working with graph instead of the image. So this is the optimal model configuration. We use residual in the future extraction with graph attention networks. In the graph construction is my own method, the ALSG. And the node characteristic is the intensity of each node, and also the spatial descriptor is the spatial location of the node in all the graph. And as you can see here, we have a stable training and test. Okay, so this is the best performance until now. So a discussion, the graph-based methods offer a transformative approach because we are working with graph. And with this, we are extracting information of the individuals, encoding the morphological feature of each individual in graph. ALCG outperformed the RAR and the KNN methods with 52 versus 46 and 48 and the validation accuracy. And the validation accuracy also is with image never seen before for the model. Okay, so this is a good performance. And the ALCG adaptability handles natural image variability effectively. Okay, this is the main approach because we want to include all the community. Everyone with a cell phone can take a photo and identify the individual, as you can see here. This is the idea. Just with your cell phone, take a photo in any way, and with this photo, obtain the specific ID of the seed total. So this is the main idea. It's effective even using a few match. If you have worked with the machine learning, you know that we need a huge database. In my case, I have a small database and I have good results. They match are taken in real life conditions, that's the idea, and ideal for marine conservation needs. As future work, integrate advanced segmentation using other models to reduce the background impact, just to have the individual and delete all the background, and explore the quantum machine learning for improve the graph. Okay? So I want to spread my gratitude to Dr. Mireya Garcia and Dr. Alejandro Ramirez for the invaluable support. Also, I want